That's fairly simple problem. You have a particle in a box, but instead of the potential energy being 0 from x equals 0 to x equals L, we're going to make our potential energy jump to some finite value V naught between L equals 4 and 3L equals 4. Okay, so it's non-zero between L equals 4, x equals 0 and x equals 3L over 4, and then it goes back to 0 after that. Okay, so V is 0 here, V is 0 to the right of that barrier. So you have a barrier in the middle of the box. Okay, and so we need to estimate the ground state energy E1. What's the zero order ground state energy for a particle in a box? E1 for a particle in a box would be n squared h squared over 8m L squared, right? And n is 1, right? So it's going to be h squared over 8m L squared. That would be your zero order energy. If the perturbation did not exist, then that would have been your energy. Since we have a perturbation here, our correction term here is E1. Is given by this formula, psi naught h prime psi naught integrate over all space. And what's our perturbation here? It's what will be our Hamiltonian in this case? Hamiltonian is going to be negative h bar squared over 2m, second derivative with respect to x. That's your kinetic energy operator. Plus your potential energy operator is V naught. But that's only applicable from L over 4 to 3L over 4. Mathematically, you can write this using a Boolean expression. You can say V naught times x greater than or equal to L over 4 times x less than or equal to 3L over 4. Okay, this Boolean expression is called Boolean expression. This is 1 if true, 0 if false. Okay? So in other words, if x is greater than or equal to L over 4, this is going to be 1. And if it's less than 3L over 4, it's going to be 1. So it's going to be 1 times 1 here, times V naught. Over here, it's going to be 0 times 1 times V naught. So it's going to end up being 0. And over here, it's going to be 1 times 0. Okay, so this is what you would call a Boolean expression. Each one of these is called a Boolean expression. It's just either true or false. If it's true, it's 1. If it's false, it's 0. So let's actually do this on MathCAD. First of all, before we do that, what would be our formula for E1 for the ground state? The first order correction to the ground state energy. What did we say it was going to be? Integral of psi 1 naught h prime, which is going to be V naught, right? Times the Boolean expressions there, times psi 1 naught, correct? To make things easy, let's just split this into 3 integrals. So our first integral will be integral of psi 1 naught times 0 times psi 1 naught dx from x equals 0 to x equals L over 4. Okay? So that's for the first quarter of the box. Your V naught there is 0, right? What's your integral from x equals L over 4 to x equals 3L over 4. So from L over 4 to 3L over 4, we're going to have psi 1 naught times V naught times psi 1 naught dx, right? And what would be the third term here? Beyond L over 4, you're going to have integral from 3L over 4 to L times psi 1 naught times 0 times psi 1 naught dx. So are any of these integrals easy to determine? What's the integral of 0? Constant, right? Derivative of a constant is 0. Integral of 0 is a constant. Constant evaluated from 0 to L over 4, that's going to be constant minus the same constant. So this is just going to be 0, right? And this right-hand term is also going to be 0. So it's really just this term. That's your first order correction. Let's see what that is. So I need to have an integral. Okay, I need to do an integral from what? L over 4 to 3 times L over 4. Integration over x, right? So what goes in that expression for your integrand? Psi naught. What's psi naught for the ground state? Square root of 2 over L times sine n equals 1. So 1 pi x. So pi times x over L. Okay. Times v naught. V dot O times psi again. Square root of 2 over L times sine of pi times x divided by L. And we can evaluate this expression. And that gives you that formula right there. Okay, it's 1/4 v naught 2 plus 3 pi over pi minus 1/4 times v naught times negative 2 plus pi over pi. That's your formula for your first order correction. Okay, let's get some actual numbers so we can get a better feel for what these are. So let's solve our let's get some numerical numbers. So let's again use atomic units. Let's just define h bar to be 1. So h is going to be 2 pi, right, times h bar. Remember, h bar is h over 2 pi. And we're going to use the mass of electron as our unit of mass. So let's assume our particle is an electron with one unit of mass. And what would be our, oops, what did I just do? What would be the energy for a particle in a box? If it was just a particle in a box with it would be our, what we would call an unperturbed system. So E1, let's call this particle in a box. So that would be an unperturbed system. The formula is h squared over A times mass times L squared. Okay, we need to define our L. Again, we're just going to use atomic units, so we're going to use L equals 1. Move this around. I have more room here. Align these. So our E1 is equal, for a particle in a box, is 4.935 units. Okay? Let's look at the situation where V naught, what if V naught is equal to 1? We're just going to define V naught as 1 unit. Okay? You can always change that later if you want to explore how things would change. But for now, let's just say V naught is 1, and I'm choosing V naught equals 1 because I would know what the correct answer is. If V naught is 1, you can actually solve this problem exactly. And if V naught is 1, I have the number for you later. Okay? So what would be our potential energy? V of x, potential energy as a function of x, is equal to 1. V naught times, what's our Boolean expression? X, okay, over here, right here, this toolbar right here, this is your Boolean toolbar. So x is greater than or equal to L over 4 times X less than or equal to 3 times L over 4. Okay, so what I'm doing here is if I multiply, if my X is between L over 4 and 3L over 4, both of these Boolean expressions will be true, then V of X is just going to be equal to V naught. If any one of these expressions is false, then the whole expression is 0, which is what I want, right? So let's plot that. So insert a graph. Planet versus X. Let's plot X from 0 all the way to L in steps of 0.01 L. So we're going to have 100 points between X equals 0 and X equals L. So I'm going to plot V of X. And what does that look like? Let's make this 2. There it is. So you can see over here, V naught is 0 from X equals 0 to X equals L over 4. Right? Potential energy is 0. Potential energy is V naught, which is equal to 1 from L over 4 to 3L over 4. And it's equal to 0 after that. Okay? So that's your potential energy function. So you have a perturbed system here. Your perturbation is V naught from X equals L over 4 to X equals 3L over 4. All right. So how do we calculate our first order energy correction? Okay. E first order. First order correction term would be equal to what? Integral from 0 to L. The nice thing about putting that Boolean expression is I don't have to separate my integral into 3 parts. So I can put everything in just one integral, dx. And what is my perturbation? My perturbation is V naught times X greater than or equal to L over 4 times X less than or equal to 3L over 4. Okay, so that's going to be what I'll type here. Let's say V naught times X greater than or equal to L over 4 times X less than or equal to 3 times L over 4. Okay, let me get rid of this. And so what would that be equal to? E first order correction equals 0.5. Is that what we're getting? That's our energy correction. Okay. Oops, wrong. That's not right. We forgot our size, right? This is just H prime. I need to have psi. What's our formula? It's psi prime. It's psi naught H prime psi naught dx, right? Integral over dx. So this is just the H prime. I forgot to put the psi, the A. So let's do that. So this one I need to multiply by, what's our psi? Square root of 2 over L times sine n is 1. So that's just pi times x over L. Okay, and then over on the other side, multiply this by square root of 2 over L times sine pi times x over L. Pi x over L. It's 0.818. So that's your first order correction. Okay? And let's verify that that is in fact what we get if we just use the formula we derived earlier. Here's the formula we derived earlier, right? Copy that. I mean, copy that whole expression right there. And Let me put that down here for comparison. You said that's the formula for the first order correction, right? I'm going to say equals, and see, you can get the same answer. You get the same answer. All right, so yeah, that's your first order correction. So what is your approximate energy then? Approximate energy would be h squared, which is E1, right? E1 for the particle in a box. That's your zero order energy. That's your zero order approximation. Plus the first order correction. So E first order correction. Okay, so this is my E1 zero order value plus E1 first order correction term. Right? So what would that be equal to? E approximate equals 5.753. And what was our original E? E1 PIV is 4.935. Okay? Now, it turns out, in fact, that let's express this in terms of h squared over 8ml squared. So E approximate is equal to 5.753 in terms of h squared over 8ml squared divided by 8 times mass times L squared. That's equal to 1.166. So it's higher than the particle in the box ground state because of that perturbation. You would expect it to be higher because there's an extra potential energy there. So your energy will be higher than the ground state for a particle in the box. Okay? Now, the known value, you can actually solve this exactly. This is simple enough. This problem is simple enough that you can solve for the exact ground state energy, and the exact value happens to be 5.750345. Okay? So what's our percent error? It's going to be approximate value minus the exact value divided by the exact value times 100, and our percent error is 0.048%, not too bad. Okay? We have a pretty small perturbation, so we have a decent accuracy here. Now, let's go back to the variation theorem. We said that if you have a trial function, if you just guess what the function is, right, for your particle, and you plug that into that formula that we had, that you get an upper bound or a value that's always going to be higher than the true ground state, right? So what if we were to do, let's say, what if we were to just take the particle in a box, the zero order wave function, as our trial function? Let's see what kind of energy are we going to get. Okay, so what's the formula for the particle in a box? Let's call our trial function phi. Okay, so we don't confuse it with the true psi. So it's going to be square root of 2 over L times sine n pi x over L, or n is going to be 1, right? So let's say that's our trial function. How would you calculate the variational energy, our estimate of the energy using the variation theorem? You can say, what? Let's first get h hat operating on phi. Function of x would be equal to what? H operating on phi for particle in a box. It's going to be negative h bar squared over 2 times the mass times the second derivative, right, with respect to x of our phi. Okay, and let's put the actual expression for phi. Okay, so that's kinetic energy operator. So this thing right here is your kinetic energy operator operating on our phi. We need the potential energy term here because we have a perturbed system. Okay. So you are going to add V of x, oops, sorry, plus V of x times square root of 2 over L times sine pi x over L. Okay, so this is t hat phi plus v phi. Okay, so this is h hat operating on phi. We're using the actual Hamiltonian for our perturbed system. So if we do that, how do we calculate the variational energy? W is going to be equal to, what was it? It's going to be this integral right here, phi h hat phi, right, divided by phi phi. That's your when you do your variational calculation. That's what you need. So let's put that in. So our numerator is going to have an integral from. Okay, so you have a numerator and a denominator. Another integral in your denominator. So what goes here? X integral from 0 to L of what? Phi h hat phi. So phi of x times h hat phi of x divided by, so this one's an integral from 0 to L dx of what goes down here? Phi of x, oops, not f, phi of x times phi x, and everything is real. We don't worry about the complex conjugate. Right? So we get that expression for W, and our W is going to be 5.753. And that's higher than the exact value, which is 5.750. But look at your approximate value from the first order perturbation correction. Your first order approximation using perturbation theory, your approximate energy is 5.753. If you just use the zero order wave function as a trial function and you did the variational calculation for the energy, you get the same number. Why do you think that is? Same number, 5.753. Well, let's take a look at it this way. Remember, our phi is normalized, so this thing down here is really just 1, right? We were using our zero order wave functions are normalized. So let's just look at this expression up here. If you have phi h hat phi, okay, let's break that up into phi h naught plus h prime phi. Well, what can we do now? We can write this as phi h naught phi plus phi h prime phi. Right? But what is this first term right here? That's just your E naught. Right? That's your zero order energy. What is this term right here? First order correction. In perturbation theory, that's called your first order correction. So you get the same answer. Okay? Of course, they're both not perfectly accurate, of course, okay? Because we are doing approximations here.